Hello, I'm Daniele Santoro from FBK and I'm going to present a demo about the application of Kubernetes Cluster Federation in fog computing. In this demo, we will interact with three user interfaces offered by the Fog Atlas framework: the topology, the application composer, and the command line interface. Let's start looking at the first one. The map shows the global vision of a distributed fog computing infrastructure. It is based on a single Kubernetes cluster controlling remote regions. The Kubernetes and Fog Atlas control plane are installed inside the master region, while in the remote region, region 1, is a group of Kubernetes worker nodes. This red line represents the network link across two or more regions and its capabilities in terms of network latency and bandwidth. Region 1 is directly connected with an emulated camera, Cam1, that is playing a video stream of random sentences. The second user interface we will look at is the application composer. It is a graphic user interface that allows users to create application models simply by dragging and dropping elements like microservices, endpoints, and data flows. In our case, the camera will be the endpoint, while the component of the application will be our microservices. Application models can be created writing YAML code. They can be imported using the import button on the left side, or simply loaded from a pre-imported list from the right sidebar. Let me open the simple OCR application, which is the reference application we will use for this demo. As you can see, it is composed by one endpoint and three microservices. The first one is the data collector, basically gets images from the camera, extracts them, thanks to use of an OCR library, and then the text is stored inside the second microservice, which is the repository. Finally, a summary is presented by the third microservice, which is a web-based graphic user interface, the web server. Using this user interface, we can specify requirements for every microservice in terms of CPU, GPU, memory, and locality. But we can also specify network requirements in the data flow connecting two microservices. For example, in this case, we set a high bandwidth and low latency constraint between the camera and the data collector, and between the data collector and the repository. When the design stage is done, a user can double-check the model components by looking at the source codes, associate the model with one of the available algorithms, and then save it. In order to deploy the application on the infrastructure, we use the Operate button. During this process, a scheduler using the chosen algorithm elaborates the graph representing the application model and finds the best place for every microservice. In this specific case, we expect it to choose a proper region for both the data collector and the repository, due to the networking constraint we set before. Once the status is deployed, we can switch in the topology graphic user interface, where we can see that the data collector and repository has been placed in the region directly connected with the camera, while the web server, which has no strict constraint, has been placed in the cloud region. Now that the web service is deployed, we can look at its interface and see that the recognized text, including some additional information, is refreshed every few seconds. At this point, we would like to introduce a network failure across the two regions by temporarily removing the link connecting them. This is done via a script from the command line. As you can see, the link disappeared and the application web server is not able to communicate with other microservices, causing a service disruption. Moreover, a user would not be able to operate anymore via the Fog Atlas application composer on the remote region, region 1, because it has been lost by the main control plane hosted in the master region. We will see how to solve this situation in the next part of the demo. Let's switch to the federated infrastructure. These second maps show a global vision of a federated distributed for computing infrastructure. We have two Kubernetes clusters and therefore two control planes that are federated using KubeFed. Control planes are installed in the host cluster, master region highlighted in green, and in the member cluster, region 1 highlighted in blue. In particular, the main cluster, in green, hosts a federated control plane and is able to control the region 1, which is composed by two traditional regions, subregion 1 and subregion 2. As explained before, the subregions are nothing else than Kubernetes worker nodes. It is important to note that in the main cluster, the master region, we have both Fogatless federated and traditional controller, while in the region 1 we installed only the traditional Fogatless controller together with its own topology interface, which is this one. Even though the single microservices have not been changed in this federated scenario, the whole application model is a bit different because unlike the previous one, now it is designed by grouping microservices into application chunks. Let's have a look at the model representing the application and the federated case using the native YAML format. As you can see from line 11, we specify an array of application chunks, and every chunk is assigned to a specific cluster using the placement directive. See line from 19 to 21. The first chunk, chunk 1, is assigned to the master region and contains the web server microservice, while the second chunk, chunk 2, is assigned to region 1 and contains the repository and the data collector microservice. Locality requirements, network, CPU, memory, etc. can of course be specified as we did before. We will now deploy the federated application, and given that we extended Kubernetes using custom resource definition, CRD, we could take advantages by using the standard Kubernetes CLI, kubectl, and this second part of the demo to deploy the new application model. While the microservices are appearing in the map, I would like to quickly explain what is happening behind the scenes. The federated Fogatless controller, master region, receive a federated application model. Chunks for this model are created as federated resources in the master region, and then scheduled in the proper cluster by Fogatless. KubeFed propagates these federated resources, these chunks, on the destination cluster. Finally, on each federated cluster, the traditional Fogatless controller takes care of the chunk by scheduling all the microservices contained within it in the best place. Now that all the microservices have been deployed, we can look if the whole application is working as expected, and by checking the web server user interface, we see that the data is successfully refreshed every few seconds, meaning that the application is working well. Similarly to what we did in the first part, we will introduce a network failure again, removing the connection between the two clusters. We see that the link disappears, and of course we have a service disruption on the web server that we can check, which of course does not get data anymore. Unlike the single cluster example, in this case, a user can use the topology interface of region 1, this interface, to check the status and restore the web server by operating directly inside the remote cluster using the CLI. So from the CLI of the region 1, we will now deploy a new web server application model using kubectl. We see from the interface that the web server has been scheduled by Fogatless in the region 1, and we can check in this second web server interface if the data is coming from the underlying application. As we have seen, the new federated solution is much more efficient and resilient than the traditional one, and permits a user to operate also if the master region is isolated from the remote one.